Hello, I'm Roman, and welcome back to the series of the videos Neural Network from Scratch. Neural Networks from Scratch in Go, where we dive into the bare bones of what is the neural network is, and we're using this book called Neural Networks from Scratch in Python. But again, as you can guess from the name of the series, we are not using Python, we're using Golang. Why Golang? Why not? And in the previous, I would say 2 videos, we started to dive into the chapter 7 and chapter 8, about the derivatives, and right now we're diving into what the partial derivative is. I thought that maybe I will fit into 2 videos, probably not. Maybe this one will be fully dedicated to understanding of the math behind this, well, remembering the math, and probably in the next chapter I will actually get back to writing the code. But right now I'm at the stage where you need to remember some of the theory. So let's go. Like in the previous, we took how to calculate partial derivative of the sum or multiplication, and that we're going to use it to calculate the derivative for our forward pass inside the neural network. Okay, partial derivative of max. Derivatives of partial derivatives are not limited to addition and multiplication or constants. We need to derive them from other function that we use in the forward pass, one of which the derivative of the max. So for example, we have a function from the 2 variables and we take in the max. So we have, as one of the subscribers told me how to properly read it in English, it's d over dx, from f from x and y. So d over dx max from x and y, it's 1 multiplied by max value. Max function returns the greatest input. We know that the derivative of x with respect to x equals to 1, so derivative of this function with respect to x equals 1 if x is greater than 1, since the function will return x. In other case, where y is greater than x, we will get returned instead the derivative of the max with respect to x equals 0. We treat y as a constant and the derivative of y with respect to x equals 0. So we can denote that as y multiplied by x greater than y, which means that 1 is if the condition is met, otherwise 0. So in case the x is greater than y, then we will return 1, otherwise 0. We could also calculate the partial derivative of max with respect to y, but we won't need it anywhere in this book. One special case of derivative of the max function is when we have only one variable parameter and the other parameter is always constant at 0. This means that we want whichever is bigger in return, 0 or the input value. Effectively clipping the value at 0 from the positive side. Sounds like real. And then this is going to be useful when we calculate the derivative of the ReLU activation function, since the activation function is defined as max between x and 0. Notice that since this function takes a single parameter, we used a d operator instead of... Okay, maybe the same guy, maybe somebody else, tell me then how to properly read it. I tried to find, but it sounds like a d, but to calculate the non-partial derivative. In this case, the derivative is 1 when x is greater than 0 as y is at 0. The gradient. As we mentioned at the beginning of the chapter, the gradient is a vector composed of all the partial derivatives of a function, calculated with respect to each input value. Composed of all partial derivatives of function. Okay, so we will take, for example, we have a function as I assume, we have a function as our neural network and the function. Then we calculating each derivative against the concrete input one by one, and then we have a vector of these partial derivatives, and that's called gradient. Let's return one of the partial derivatives of the sum operation that we calculated earlier. So we have this x, y, and z. We have 3 inputs, so it means that we should have the output of 3. We should have the vector of the length 3 with partial derivatives for x, y, and z. So this is what we have. Right? Am I right? If we calculate all of the partial derivatives, we can form a gradient of the function using different notation. It looks as follows. Okay, so this is the gradient nabla, inverted delta symbol. So the nabla. So we have the d over dx, d over dy, d over dz from this function that gives us the partial derivative for each input, and that's we have the vector of we have this vector. We'll see how we're going to use it. I'll make it bigger a little bit. We'll be using derivatives of a single parameter function and gradients for multivariate functions to perform gradient descent using the chain rule. In other words, to perform the backward pass, which is a part of the model training. How exactly we will do that is the subject of the next chapter. Okay. The chain rule. During the forward pass, we are passing the data through the neurons, so from the input to output, then through the activation function to form a desired output, well, to kind of normalize the output, then through the neurons in the next layer, so the activation function for the specific layer, then through the neurons in the next layer, then through another activation function, and so on. By calculating a function with input parameter, taking an output, and using that output as the input to another function. For this example, let's take 2 functions f and g. Okay, so the y value is function g from function f from x. So x is the input data, d is the output of the function f, but also an input through the function g, and y is the output of this function. We can write the same calculation as this, so it looks like the neural network. So the x is our input, for example, the first layer, that is the second layer, something like this. In this form, we do not use the intermediate z variable, showing that the function g takes the output of the function directly as an input. It doesn't differ much from the above 2 equations, but shows an important property of a function's chained this way. Since x is an input to the function f and then to the output of the function f, the output of the function g is influenced by x in some way, so there must exist a derivative which can inform us of this influence. The forward path through our model is a chain of the functions similar to these examples. We are passing in samples, the data flows through all of the layers, and activation functions to form an output. Let's bring the equation and the code of the example of the model in chapter. Yeah. Yeah, it actually calculates the law. Coffee Forward has an example neural network. If you look closely, you'll see that we are presenting the loss as a big function or a chain of functions of multiple inputs, input data, weights, and biases. So, for example, yeah, we have chain of functions. At some point, we have the input and the input first layer and first biases. Then we have, it's like a matryoshka. The input is inside, and you kind of go more out and out. Now passing input data of the first layer, where we also have the layers, weights, and biases. Then the output flows through the relo activation function and another layer. So basically, relo activation function in this case is taking the maximum value between 0 and the result. Right? And another layer which brings more weights and biases, and another relo activation up to the end, the output layer, and the softmax activation, where we have, the softmax. The model output, along with the targets, is passed to the loss function, which returns the model's error. We can look at the loss function not only as a function that takes the model's output and targets as parameters to produce an error, but also as a function that takes target samples and all of the weights and biases as inputs. If we change all the function performed during the forward pass, as we are shown in the images. To improve the loss, we need to learn how each weight and bias impacts it. How to do that for a chain of function by using the chain rule. The rule says that the derivative of a function chain is a product of derivatives of all the function in this chain. What? Let's try it again. Derivative of a function chain. So we have I would refer to the derivative of the network in our case is the product of derivatives of all the product of derivatives. I mean, what they mean by product? It's like the matrix product. For example, we have a d over dx f from g from x. First we wrote the derivative of the outer function, this one with respect to the inner function g, as this inner function is its parameter. Next, we multiplied it by the derivative of the inner function g from x with respect to its parameters. We also denoted this derivative using two different notations. First three functions are multiple inputs. The partial derivative of this function with respect to x is as follows. We can't use the prime notation. To calculate the partial derivative of of a chain of functions with respect to some parameters, we take the partial derivative of the outer function with respect to the inner function in a chain to the parameter. Then multiply this partial derivative by the partial derivative of inner function with respect to more inner function in a chain. Then multiply this by the partial derivative of the more inner function with respect to the other function in this chain. We repeat this all the way down to the parameter in question. Notice, for example, how the middle derivative is with respect to x, h from x did, and not as y. Now is the chain to parameter. So we're going through all the partial derivatives with respect to, I mean, we should always have the x somewhere, right? So we're not interested in the, for example, derivative. No. 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 The chain rule turns out to be the most important rule in finding the impact of singular input to the output of a chain of functions, which is the calculation of loss. We'll use it again in the next chapter when we'll discuss the encode backpropagation. For now, let's cover an example of the chain rule. Let's solve the derivative for this one. The first thing that we can notice here, we have a complete function that can be split into two simpler fractions. First is an equation part contained inside the parentheses, which can be out. They want to do it like this, okay, because I mean you can open the parentheses here, but okay, that inside function that we exponentiate and multiply with the rest of the equation. The remaining part of the equation can be written as y in this case is what we denote as g from x, and then we combine it back where we get h from x is f from g from x, and this one. To calculate the derivative of this function, we start by taking that outside exponent, the 5, and place it in front of the components that were exponentially contiguous at 50, then subtract 1. Okay. So yeah, but we assume that this is the param, like the input param, right? Then the chain rule informs us to multiply the above derivative of the outer function with the derivative of the inner function, which gives us to multiply the above derivative of the outer functions of this one to multiply with derivative with the inner function, this one, right? Okay, to here it will be 1x. That highlights the chain rule concept and example, allow us to calculate the derivative. So we're always taking the we have a function, the outer function, we take in the derivative of this outer function, then we multiply it with the derivative of the inner function, and so. Okay, maybe that will make me. So we have this, right? So we take in the first derivative of the outer function, then we will multiply it by derivative of the inner function, then we multiply it by the derivative of the inner function. And we take in the by. Okay. Now that we multiply the derivative of that interior function but left the interior function unchanged within the derivative of the outer function. I mean this. In theory, we could just stop here with a perfectly usable derivative of the function. We can enter some input to this and get the answer. That said, we can also go ahead and simplify this function for more practice. Coming back to the original problem so far, we found to simplify this derivative function, we first take and distribute the. Yeah, that's what I was telling. Yeah, but it will be the same, right? So we'd have simplify the oh, that's the simplification of the derivative function. But what if I will open? Okay, I will open the parentheses here, right? So we have okay, let's calculate the constant. 15 multiplied by no, that will be different. Oh, wait, this one. Bit 3, right? Multiplied by 32. And here we'll have x in power of 2 multiplied by 10 minus 1, it will be 96. Where did it took the... Oh yeah, and I need to... Yes, so yeah, it will be 3, 2, and 10. That's the power that goes outside. Okay, so if I will open the parentheses, it will be the same, because it's the original thought why we would do this. But okay, we'll simplify the derivatives later. For the faster computation, there is no reason to repeat the same operation when we can solve them in advance. Hopefully now you understand what derivatives and the partial derivatives is, what the gradient is, what the derivative of the loss function with respect to the weights and bias means, and how to use the chain rule. For now, these terms might sound disconnected, but we're going to use them all to perform gradient descent in the propagation step, which is the subject of the next chapter. Summary. Okay, let's go over the summary. that will be the short video, and I will make the new one starting with the backpropagation. I think it would just make more sense in terms how we would split the videos. So I'm finally done with the math behind, and we can, in the next one, we can finally do some coding. Let's summarize the rule that we have learned in this chapter. The partial derivative of the sum with respect to any input equals 1. What? The partial derivative of the sum with respect to any input equals 1. I mean, I don't understand this, but this kind of confuses me because, yes, this is the sum of the two. Well, there is a function from the two params, and if, for example, we take d over dx from the x, it means this one is constant and this is transformed into 1 because it's just a linear function. And same here if you ignore the x. But what it would be the quadratic function here, that will mean that d over dx will be 2 multiplied by x. This is why I'm a little bit confused by this. The partial derivative of the multiplication operation with two inputs with respect to any input equals to the other output. Okay. Yeah, so here we treat it as 0, right? Here we have it as a different because we have it as multiplication, so this returns into 1 and leaves us with the second one. Well, because, well, actually you treat it as a constant. It means that it should be, do I have to think here? Yeah. So it should be written like y multiplied by x, and then we take in the derivative from the x and treating y as a constant. That gives us 1 because the derivative from the x value is 1. So then it would be like this, and this is why it gives the other input. But the interesting that, for example, if it will be, for example, it will be this, right? So then we will have the 3 partial derivatives, and one will be like, for example, for the x, we'll have this one, and then the other combinations. The partial derivative of the max function of the two variables with respect to any of them is 1 if this variable is the biggest, and 0 otherwise. So for example, max from, if we take the derivative over x, over dx, then we have the variable itself if this variable bigger than the second one, otherwise it will be 0. The derivative of the max function of a single variable and 0 equals 1 if the variable is greater than 0, otherwise 0. So derivative of the chained functions equals the product of the partial derivatives of subsequent function. So we have derivative of the derivative of the, the first layer, the first onion layer over the inner value. So then we calculate, so we have the derivative of this and the function inside, the whole function inside, then multiplied by the derivative of the inner function. And if it's the same applies to the partial derivatives. So if we have function inside function, so we have the derivative of the but very interesting if we will need to find the partial derivative for the over dy. I guess it will stop here because that will, I don't know, I don't remember really. The gradient is a vector of all possible partial derivatives, an example of triple input function. Triple kill. So yeah, we have nabla that shows the gradient. Then we have three input. Well, we have three variables, and we take in the partial derivatives with respect to each variable, and then it gives us the vector of the derivatives, right? Chapter code for the resources and errata for this chapter. Okay, let's take a look. And nothing here yet. Nice. I like this. I like this part. Okay, I will stop for now. In the next chapter, it looks like we finally go into the backpropagation and we see some code. So the previous two chapters were like remembering the math, and if somebody thinks, why do I need math to do software engineering? Well, you can show them these two videos, because this is, we spent, I think, 2 or 3 videos discussing the derivatives, and that is just a small part of it. But for now, thank you for watching, and I see you tomorrow. Bye bye.